Thanks for the introduction and invitation to Rome. Yeah, so I'm working in free probability theory, and free probability allows to deal with the asymptotics of matrices, and we can deal usually with matrices, sums and products and polynomials in them. But from the machine learning context, there is of course coming something in addition, which is not part of the usual matrix stuff you're doing, namely the component application of those nonlinear functions. Huh? Okay, and I mean nowadays nobody can ignore machine learning, so whenever you see something going on there, maybe you should try to get an idea. So I'm trying to understand somehow, what is going on in this direction of applying a nonlinear function to the entries of a random matrix. Huh? So maybe my hope was to put this maybe a bit into free probability context or whatever, but or to understand this better. Huh? Okay, so I mean, what I want to understand is I start with a random matrix, and then I want to apply a function, typically a nonlinear function, to the entries. Okay. And because usually I'm working on a combinatorial level, the moment methods, okay, I will stay with a polynomial, applying polynomial to the entries so that you can calculate more or less everything. And then I want to apply a nonlinear function to this. So for my matrix X, I want to get a new matrix Y, which is given in this form here. So I apply phi. Of course, I mean, I scale my entries. So usually, I mean, I'm considering a sequence of matrices which have a limit behavior, so they scale somehow with n, and typically the entries are of the order 1 over square root of n. So I scale this and then apply my function. Then I'm going back to the scaling. And also I put the diagonal equal to 0 because otherwise the diagonal would dominate everything. So I should get rid of this. Good. Okay. And then the question is, so what is the effect of such a function? And what I'm usually interested in is the eigenvalue distribution of a function. So the question is, what is the asymptotic effect of how does the eigenvalue distribution of the matrix X change if I apply this nonlinear function? Okay, and of course, I mean, I must make some assumptions about my random matrix. I cannot just take any matrix. And of course, there was some previous work which inspired what I'm looking at. And I mean, this is either on a level of kernel matrices, or maybe on a level of covariance matrices. And I mean, I was particularly inspired by this work of Pennington and then also Piccolo and Schröder. But I mean, the setting which is there is usually of a quite specific type. You have Wishart type of matrices, the product of some Gaussian matrices. And I mean, my main message is that what you have here is actually seems to be more general, and it just relies on the fact that you have very specific random matrices which have some invariance property. So the setting which I will consider are orthogonal invariant random matrices. Okay, and of course, I mean, so how are they given? I mean, there's of course matrices which are considered in many contexts, in physics, but also in free probability. That's the typical matrices which are becoming asymptotically free. And I mean, if you really want, I mean, either usually very often in physics also, I mean, they are given by a density. So if Xn is your matrix and dXn is the product of all these of the entries, then you have a density, and here you take the trace of a function of your matrix. This is then responsible that you have an orthogonal invariance, or you can also have multi-traces, so you can have product of various traces here. I prefer to present, or at least create such matrices on a computer by just taking polynomials in independent GOEs. GOEs, the Gaussian orthogonal ensemble, those are the most basic random matrices, which give rise to the semicircle. But then if I take several of them, I can also take polynomials in them. Okay, so here I have independent GOEs, and I take polynomials in them, and this creates an orthogonal invariant matrix. And in such guys, I'm interested. Good. Okay, and then what are the properties of such this class of matrices. As I said, of course, they have this orthogonal invariance. This means they don't have a preferred eigenvector direction. I mean, if you rotate this ensemble, then it's the same. So the same means the joint distribution of the eigenvalue of the entries does not change. Okay, so there is no specific direction for the eigenvectors of such guys. Okay, so for any orthogonal hole, this is the case. Good. Okay, and then of course, I mean, you also have to do some scaling. And of course, I mean, for the GUEs, you do the usual scaling. And also, when I gave you the density exponential, then there was an n in the exponential, which means that you have a limit. Usually, I have a sequence. For each n, I have a matrix. I have a sequence of them. And if n goes to infinity, they have a specific behavior. And what we actually have is that we have, if we calculate the information about traces of powers of the matrices, that's the macroscopic quantity you're interested in, then they scale in a very specific way. Okay. And so what I'm looking here at is actually the classical cumulants of traces of powers of the matrices. Okay. And I mean, the classical cumulants, I mean, the first cumulant is the expectation, the second cumulant is the covariance, and then, of course, you have the higher cumulants. And all those guys have a very specific scaling. So namely, I mean, the expectation, so actually the scaling is with n to the n minus 2, where n is the order here. So for the first one, it's just 1 over n. So I usually, the trace here is the ordinary trace, the sum over the diagonals. So we have to scale this by 1 over n. This is got some information which survives in the limit. For the covariance, I mean, we have the scaling n to the 0, which means we just take the covariance of two traces without any scaling. That's the quantity which really has it's the leading order and limit, and so on for the higher ones. Good. Okay. So, and this is somehow, those are my matrices, and I'm looking on, and they have this very specific behavior of the cumulants of traces, and this has the effect that. What is the effect on a microscopic level? Because I mean, I apply now my F not to the matrix itself, but to the entries. So I should somehow understand what does this mean for the entries. This is a description on a macroscopic level where I tell you what is the behavior of the traces. That's usually what I mean, the trace of powers is what I need if I want to calculate the eigenvalue distribution of such a guy. Okay, but if I want to apply my function to the entries, I should understand what do I know about the entries. And this macroscopic behavior for the traces means that if I'm looking on the entries and I'm looking there on the cumulants, again, I have a very specific behavior. So namely, this orthogonal invariance means that actually there are, I mean, I have many I have n squared entries, and cumulants, I have a huge amount of cumulants, but actually only a few of them have information about the leading order. Okay, so I mean, I'm looking on those, and only indices, such cumulants where I find some cycle structure in the indices which I have here, they are non-zero. Okay, and so the leading order guy is given if I have, I mean, I have here I and j, all different, but in most cases they are 0 or very small. And the guys which really are the leading order in the limit are those guys where I have here I1, I2, and then the next side has I2, I3. So like I have it in the matrix multiplication, and also the trace. So I1 is also showing up here. Those are the cumulants which the entries of my matrix, which have the main information, and actually they go with this order. Okay, and actually because of the orthogonal invariance, actually their value does not depend on the choice of the indices. So for all choices of the indices, they have here the same value. Good. Okay, and then I mean, of course, there are other quantities which also have are not necessarily 0. So I mean, I could find more cycles here in this index structure, and they have a leading order which goes with a lower quantity. So you see, I mean, here I have 1 minus n, but if I have r cycles here, then I have 2 minus r minus n. So this has a smaller leading order. Okay, and of course, maybe you should also take into account that, of course, if I write it like this should be seen as modulo the operations which I can do with the entries which I have. Of course, I have classical random variables, so I can permute the arguments of my cumulants, and I also consider symmetric matrices. Okay, so I want to consider symmetric orthogonal matrices, which means that, of course, xij is the same as xji for my matrix. And this means if I say I have a full cycle here, then of course I'm allowed to make these permutations of the arguments and also the permutations of the ij index. So this means, for example, with a cumulant like this, which doesn't look like a cycle in this form, of course I can exchange it. So I can bring the 2, 3 to the second position. And then, I mean, it's still not yet this, but I can then also exchange the x14 to x41, and then it has this cycle. No? Okay, so I mean, this has also the same leading order as this. Okay, so those are the guys which somehow dominate the microscopic information. So they are the information on the microscopic level on the entries, which I have. And yeah, okay, maybe before I continue on this, the question is also, where does one find such statements in the literature? Because, I mean, those things are somehow known on different levels, but in particular in the orthogonal case, it's maybe not so clear. So, I mean, for the unitary invariant case, the complex case, I mean, such results in the mathematical literature, I mean, go back to Saint-Justin or Collins or Lyonnais, at least for cycles of this form. If you have more cycles, then in my paper with Benoit Collins, Jamie Mingo, and Piotr Sniadi, we work this out in full detail. For the orthogonal case, this is not so clear. I mean, there's this paper by Capitaine and Casalis, but this is only on 1 or 2 cycles. And the question is, I mean, is this anywhere written up? I mean, in this paper, which I'm talking about here, I have somehow what I had here in this paper for the unitary case. I have rewritten this in an orthogonal case. Of course, the orthogonal case is always a bit more complicated. So essentially, you prefer to cite something instead of doing it by yourself. But anyhow, so what I needed, we have done there, but it would be nice to know whether there is actually more there, maybe also in physics papers. In particular for the case of several cycles. Right? I mean, there is this paper of also Florent here a couple of years ago, but it's a physics paper, and I'm not really sure how much is concretely there. I still have to read this maybe more carefully. Okay, but in principle, I mean, we have done this in this paper with Alexander Velli, which I'm talking today. Good. Okay, but now so the question is now. So what do we have here? So I have my matrix X, my orthogonal invariant matrix X. I want essentially, I mean, I want to understand its macroscopic, its eigenvalue distribution, but I mean, the crucial information which I'm going to use later is the microscopic information about the entries. And this information about the entries is mainly encoded in this cyclic cumulants of such a full cycle. Okay, and this means these are quantities which are really irrelevant, which contain the main information, and so maybe let me call them kappa n. So I have here the nth cumulant with the right scaling, and then I take just such a cycle, and as I told you, which indices I use here is not important because it's always the same. Okay, and the relevance of these microscopic quantities in context with the macroscopic eigenvalue distribution is of course given by the fact that, I mean, for the calculation of the moments of my eigenvalue distribution, I have to calculate the expectation of the traces of some powers. This, of course, I can write in terms of the entries. Okay, and now I can use the classical moment cumulant formula, which allows me to express the expectation in terms of the cumulants. So C pi is here a product of cumulants, and I have to sum here over partitions of n elements. That's a classical formula how you connect the moments with cumulants. Okay, now you have to sum over all partitions in n. Okay, but now if you plug in this information which you have about the orders of things appearing here, then many terms will disappear, at least in leading order. And actually also, I mean, here you're summing over all partitions, but yeah, the structure of these 8 indices here will in the end lead to the fact that only partitions which are non-crossing will survive. No? They will only make a contribution. And their contribution is exactly given by this kappa pi, the product of those cumulants of the entries. And so what we get here in the limit is now exactly a moment cumulant formula from free probability, which connects moments, but now with free cumulants. Okay, so this tells me that the kappas, which I have defined here as the classical cumulants of the entries, are actually the free cumulants of my matrices. Okay, the free cumulants are the corresponding objects which we have in free probability theory, which are given by a formula like this. Okay. So this means exactly this, that yeah, the microscopic information about the entries of my matrix, they contain the information about the free cumulants of my matrix. Good. Okay, so that's about the axis. That this is my very nice orthogonal invariant matrices. But now I want to apply my functions. So now I'm coming back to my main problem. So I consider now such an orthogonal invariant matrix where I know essentially what the information about the entries, what this has to do with the information about the eigenvalue distribution. And now I apply my nonlinear function here. And as I said I take away the diagonal, and actually I should also take away the off-diagonal entries. Okay, because if I apply a function, I might also get a mean there, and this would produce one big eigenvalue which would shift things. So better is also subtract this away. So this means yeah, expectations of the entries, they are cancelled. Good. And now the question: what has changed if I'm going from the x's? The x's are the very nice matrices, orthogonal invariant, and the y's are the one where I have applied my function f. And the question is, can I still say something about the y's? Of course, they are not orthogonal invariant anymore, because applying functions to the entries, this is like going over from Gaussian to Wigner matrices. Okay, so I keep somehow something between the entries, but I'm changing the entries. So they are not so nice anymore, but still they have enough structure that more or less I have the same relation between macroscopic and microscopic. So again, it's the case that it's only those cumulants with a cyclic structure, they make a contribution in the limit if I calculate this expectation of the traces of a power. So in the end, I have the same formula as before. There are other terms, there are more terms that are not zero than for the x's, but asymptotically they don't contribute. So this means I still have this relation here, that those guys here, namely the cumulants of the y's, where here all the entries are given in this form, and maybe I should put them all distinct. Before it didn't really matter so much whether they were distinct or not, but here it makes a difference. And the other ones might not actually be the same, but they don't appear here. So here in this sum, it's also really the ones which come here from distinct indices. Okay, so those are the quantities which are important. And again, I have this formula, which means that again, those guys here are still the free cumulants of the eigenvalue distribution of the matrix Yn. So I have not the very nice symmetry for the y's, but I still have the same statements as before, namely the eigenvalue distribution of the y's is given by free cumulants, and those free cumulants I can read off from the cumulants of the entries. So this means if I want to understand what happened to the y's, what is their distribution, I should understand what happens to the free cumulants of the entries. Good. Okay, so the question is now, how does f change those cyclic cumulants of the entries? So what I have to understand are those guys here, the y's. And the y's, of course, are now the functions of the f's. And now, of course, I mean, I should go back from the y's to the x's. So maybe I should take a polynomial, let's say, and then, of course, I can plug this in, and then I have a multilinear expansion. And you see in the end, I mean, what I really have to understand are the cumulants, where now the entries are not the x's, but powers of the x's. The powers coming from the f here. Huh? Okay, and I have to see what happens with those guys. And of course, I get some scaling here, which comes from the function here, because I also scale this in a way. And I have to understand the leading order of those guys. And I mean, I know the leading order of my orthogonal invariant matrices was n group the 1 minus n. So I mean, this should also have this order if things work out. Good. Okay. So this is the question. Yeah, I have to scale this in the right way here. So I have to scale it. With this here, and see what is this asymptotically. So the question is, I mean, what I know are the cumulants of the x's with those indices, but without the powers. That's my input. That's what I know from my matrix X. And now I take the powers, and the question is, what can I say about this? Okay, and for this, there's a classical formula about for cumulants, classical cumulants, where you have the products as entries. Okay, I mean, this is maybe a bit tough to read, but essentially it's a combinatorial formula. So I mean, maybe let's just look at this example. So I want the second cumulant. So it has two arguments, but now the arguments are products of variables. And I want to reduce this to the cumulants where I only have a's as arguments. And then this formula of Leonov and Chelyabinsk tells me that what I should do is, for calculating this, I should sum over partitions, classical partitions, which connect more or less those four guys here, but the guys which are multiplied are essentially already connected. So this means, I mean, I can of course connect everything, and for this I get this contribution. So this is a fourth cumulant where I just put in all the entries. But I can also take this, because I mean here I'm connecting those two blocks. So I mean this and this together connects all four. So I also get a contribution from this. And here I have two blocks. So I take here a product of two C2s, and each of the C2s gets the arguments which are corresponding to this block. So one gets the A1 and A4, and the other gets the A2 and A10. And then I have this one, and then I have more. But if I don't have singletons, then I don't have more. So I hope the structure of this formula is somehow clear. So I mean, I can reduce it to cumulants where the a's appear just separately as an argument, but I have to sum over all possibilities for connecting those guys. Okay, this formula I have to use to understand how the cyclic cumulants of the y's are changed, or how they depend on the ones of the x's. Good. Okay, so what we have to understand is the Cn. I mean, I have here the y12, the y23, yn1, let's say, but they are powers of the x's. And so I have to understand what is this. And now this formula of Leonid and Chelyabinsk tells me that I have to sum over partitions where I actually connect. I mean, this is just a way of writing it. I should connect those n blocks together. Okay, and so what I need here are actually pi's, which connects the groups. So we must be all connected. And then, because I'm only interested in the leading order, the blocks should be as small as possible. Because I mean, the smaller the block, the smaller the order. And because the order of, if I have a block of size n, then it was n to the 1 minus n. So if I have smaller blocks, then the order is better. And of course, the leading order is the one where I have blocks as small as possible. Good. Okay, so I have two conditions. I should make the blocks as small as possible, but I still should connect the groups. Okay, and then of course, I mean, singletons would have the biggest order, and so but I have excluded them because I have set the diagonal equal to 0 and subtracted the mean. So singletons, which means a block of size 1, don't show up. So the smallest blocks which I can have are pairs. Okay, but in general, I mean, I'm not able to connect those guys with pairs, because I mean, if I go from this group here to this group here, you see I have different variables for which the covariance is equal to 0. So this means in order to satisfy this connectivity condition, I need at least one block which connects all those groups. So because that's the only way how I can connect them. So this means I should have at least one block which connects all of them, and then hopefully the rest I can do with pairs. Okay, and maybe, yeah, this is the case, but the case n equal to 2 and n bigger to 2 is somehow different, and n equal to 1 is trivial because there's everything 0. But maybe let us first think about whether having something like this gives the right order. So we're looking on this, and then we also have to scale it with this. And then I told you I need one block, at least one block of size n. This has order n to the 1 minus n. And then the rest, hopefully, I can do with blocks of size 2. A block of size 2 has order n to the minus 1, but then I have m minus n over 2 left. Yeah, I mean, I have a block of size n. So I mean, I have here m arguments altogether. Okay, I have one block of size n, so I have m minus n elements left, and I divide them into so many blocks of size 2. Each of them has this order, and if I take all this together, then actually you see this really is the order 1 minus n, and it should be. Okay, so it's really, I mean, I really should hopefully be able to do it with one big block and the other just pairs. Of course, I could take more big blocks, but then the order is smaller. Okay, so the order seems to be okay. So let us see whether we really can get something like this. And so let me here look on 4. Okay. So what I have here, so this is the cumulant, where I have here some products of x1,2s, then x2,3s, so on, up to x4,1s. Okay, now how can I do this? I said I need one block of size 4 in this case. Okay, so I mean, because then this is a cyclic guy. So this is 1, 2, 2, 3, 3, 4, 4, 1. So this is which has a leading order in the axis. And the contribution of such a block is a kappa 4 here. Because each block contributes with a kappa, and the index is the size of the block. Okay. And then, of course, I mean, I also should count the possibilities. How many possibilities do I have to choose such a block? Okay, and I mean, this block must have one element in the first group. The first group has M1 element, so I have M1 choices for this. For the second guy, I have M2, and so on. So this is somehow the choices which I have for choosing this first block. This block of this big block, and it makes the contribution kappa 4. And then for the rest, what can I do with the rest? Now I want to do pairings, and of course I cannot pair this guy with this guy, but inside these guys here I can pair, because I mean x1,2 is the same as x2,1. So I can pair an x1,2 with an x1,2. So that's okay. Right? So this means now the problem is that I should now pair within those groups the rest. Okay, and how many possibilities do I have there? Yeah, I mean, I have to sum over all pairings of those guys, but actually calculating the pairings of something is calculating a moment of a Gauss distribution. So I mean, I have here M1 minus 1 elements left, which I want to pair, and instead of writing it as a number of pairings, I say this is the same as taking the expectation of a Gauss variable to the power m1 minus 1. Because this expectation is counted by the number of pairings. And then, of course, it should have the variance kappa 2, because each of the pairs make the contribution kappa 2. And here the same. So you see what I get for those guys is really this contribution here. Okay. And now, of course, this G here, I mean, G is my function. G is here, this function, x to the power m1. Okay, now you see I have here, nonsense. G is the Gauss variable, but here I have this function here, m1 minus 1, and here I have the m1. So you see what I have here is exactly the derivative of my function. So I can also write this as the expectation of the derivative of f1, and f1 is now x to the power m1. F2 is x to the power m2, and so on. So I can write it as this here. Okay, and so this means the contribution which I get here is exactly that I have a kappa n, and then I have here, if I take now my function here, if I take here the same function, then you see I get here just n times the expectation of f prime of g. Okay, so that's now the corresponding cumulant of the cyclic for the cyclic indices for the y's. So you see, I mean, this are the y's, and you see essentially I have changed the cumulant of the x's, that's this kappa n, here by a factor, which of course depends on my function f, but only a very little information. Okay, this is true for n bigger than 2, and for n equal to 2, the situation is somehow different, because now you see that actually, now of course I can connect from here to here, because I have here 1, 2, and I have here 2, 1. So I can even connect with pairs. And now of course the long block is now also just a pair. So what I get here is just, I mean, I connect from one side to the other, and then I just connect the rest by pairs. I connect everything by pairs. But this is just doing the same as taking the covariance of the corresponding function of a Gaussian random variable. Okay, so for the second cumulant, for the y's, I get not a change as before of the kappa 2, but I get somehow the C2 of f of this. So you see that the second cumulant and all the other ones are changed in a different way. Good. Okay, so here's again a summary of the changes. I mean, the first cumulant I have put to 0, and the second one change is given in this form, and the higher ones are given essentially by rescaling the cumulants of the x's. Okay, and now you can say, okay, now I have here the cumulants, and if I want, I can calculate maybe the eigenvalue distribution, but usually maybe that's not a good thing to do. I mean, you can say this is the R transform. I write down the formula for the R transform and the Cauchy transform, but this is an equation which usually you cannot solve. But if you have this structure of the cumulants, you see very easily that you can write down another model which has the same cumulants. Because I mean, what we have done here is very simple. I mean, we just have rescaled. I mean, if I only have this, then you can say I just have multiplied the entries of the matrix Y just by this factor. Because I mean, for each cumulant, I get exactly this factor. So this is just the rescaling. And the only point is that for the second cumulant, this is not true. So this means I get a rescaling of my matrix, and then I have to repair the second cumulant. But just changing the second cumulant is very easy, because I mean, the second cumulant is something which is only there for semicircle distribution or for GOA. So this means I can make a change like this, then I have by just rescaling my matrix, then I have done everything right. But for the second cumulant, I just add the GOE, which repairs the mistake which I have done on the second level. And so this is what usually goes under the name of a Gaussian equivalence principle, namely that my matrix Y, which was this nonlinear matrix, I take this matrix X, apply F entry-wise. This matrix Y has the same asymptotic eigenvalue distribution as a linear model, where I just rescale my matrix. This was just this factor. This takes care of all the cumulants, but the second one, and for the second one, I'm just adding a standard GOE. And of course, this θ2 just repairs the difference on what should happen for the second cumulant. Okay, so this is this equivalence principle that really, I mean, this nonlinear random matrix is actually just a linear matrix. The effect of the nonlinearity is adding some noise, essentially, in this very general setting. Okay, now let me look on some examples, just to check it numerically. And maybe let me take as a function the ReLU function. Of course, this was just for polynomials, but still, of course, one believes things that it should be true more general. So let me take the ReLU function. Then I should take an orthogonal invariant random matrix. And as I told you before, I like to produce them as polynomials in independent GUEs. Huh? So here I take two independent standard GUEs, A and Bn, and then I take here kind of quadratic polynomial in them. Huh? So this is an orthogonal invariant ensemble. Okay, and then the Gaussian equivalence principle, I mean, I don't want really to calculate. I mean, I could calculate this machinery of such a thing, but what I want to do is numerically to compare two random matrix ensembles, namely the one where I apply entry-wise the Reno function to the xn, and then I take this linear Gaussian equivalent, which in this case is 1/2 xn, and then the adding of this set n. I mean, here you can calculate this θ1 and θ2 very explicitly. Okay, and so here picture. So I mean, this is the eigenvalue distribution of this matrix here. And then, I mean, applying Relu entry-wise changes it to this. Okay, and then the Gaussian equivalent is given by this, and now I also calculate this, and in order to compare, I superimpose the two histograms, and I hope you see that this fits quite well. Huh? So the Gaussian, the linear equivalent has the same eigenvalue distribution as the nonlinear function. Okay, good. Here, okay, I use the Reno function, and maybe, yeah, one can say the Reno function is more or less is a linear function, also at least a piecewise linear. So maybe this is maybe not really so nonlinear. So maybe I should also take a more nonlinear function. So now I do the same with again the same orthogonal invariant matrix, but now I'm applying entry-wise this function here. So comparing this, and of course the coefficients here have changed. And if I'm comparing this, I get something like this. Okay, and maybe you say that you see at the boundary, okay, it doesn't fit so well. So I think this is really a large n behavior, which if n goes to infinity should disappear, but actually at the moment I'm not so sure about this. Okay, but maybe if you do this approach, you can also extend this to multivariate situation. I mean, the nice thing of doing things combinatorially is that arguments for one variable and for several variables usually are the same, or very often you can extend it. You just get an extra index somewhere which is not affected by the arguments. And that's the case here. So you can extend this to the multivariate case. So instead of considering the function of one matrix, we consider now a function of several matrices, let's say two. So I take now two independent orthogonal invariant matrices, x1 and x2, and I take now a function in two variables, and then I apply this function entry-wise to the two matrices. So I take the same ij entry from the first matrix and from the second matrix, again subtracting the mean. And again, you can do the same arguments as before. You see the change of the cumulants and so on. And again, you have this Gaussian equivalence principle, namely that this nonlinear random matrix has the same asymptotic eigenvalue distribution as a combination of the two matrices, and then you are adding a noise. And I mean, again, this θ1 and θ2 is just taking care of changing all the cumulants, but the second one, and now of course, before you had the derivative, now you have, okay, you have two variables, so you have two derivatives for this, and the theta here corrects just the second cumulant. Okay, and maybe again, example, maybe what is a nice function of two variables, maybe the maximum function, let's take it here, and so now I consider two orthogonal invariant random matrices which are independent. So again, I mean, I produce them out of independent GUEs. I have A, B, C, and E. So they are independent GUEs. The first matrix is built out of the A and the B, and the second is built out of the C and the D. So each of them is orthogonal invariant, and they are independent. And then, I mean, I apply now the maximum to those two guys, and I compare it with this Gaussian equivalent, which is now of this form. Okay, and again, I mean, here are the eigenvalue distributions. So this is the eigenvalue distribution of the first matrix. This is the eigenvalue distribution of the second matrix. And if I apply now the maximum function, so I take the maximum entry-wise of this and this function, then I get an eigenvalue distribution like this. And I mean, if I do this linear equivalent, I mean, I get something which looks the same. And maybe if I put them together in some pictures, it's even clearer. Okay, maybe again, one can say the maximum function is also a quite linear object. So maybe I should also take something more nonlinear, a function in two variables like this, taking the same matrices here. And then I compare this with the Gaussian linear equivalent. And again, here is the superposition of the two pictures. And again, you see at the boundary of the spectrum, there are some. Yeah, I'm not sure. This suspect it goes to 0 if n goes to infinity. Okay, but yeah. Good. Okay, and then maybe finally, if I look on two matrices, why not allowing correlations between them? And again, this doesn't change much. So instead of taking two independent matrices, each of which is orthogonal invariant, I just take a pair of matrices which is jointly orthogonal invariant. Okay, and so then of course I get correlations between the entries of my matrices. Okay, but again I can take a function of this and ask what happens there. And again, the arguments are the same combinatorially. I mean, this correlation doesn't change much. So essentially, this nonlinear random matrix model has the same asymptotic eigenvalue distribution as this combination of the two matrices, and I'm adding a noise. And of course, this θ1 and θ2 is again calculated from this here. And now on the second level, I have again to correct to get the right covariances. So, and of course, the Gaussian variables which I put in here, I mean, they also have now the covariance of the two matrices from which I start. Good. Okay, and so maybe I'll do it again for the maximum function. And yeah, how do I take orthogonal invariant matrices where I have a correlation? I again build them out of independent Gaussian matrices, but now I use some of them for both matrices. So again, I have here A, B, and C as my independent standard matrices, GOEs, but you see the A's I have now, it appears in X1 and in X2. So this means I have a correlation between those two matrices. Okay. Yeah. And again, I can compare the nonlinear model, the maximum of the two matrices against this guy here. Okay, and this is done here. Okay, so this fits also quite well. Good. Okay, so this was more or less what I wanted to say. Maybe still, yeah, you saw maybe questions which canonically come up. So I mean, of course, I presented you polynomials. Of course, pictures I showed you for more nonlinear guys or for non-analytic functions. And of course, we expect that this is true for more general functions, but we have not really addressed this up to now. But this is, of course, something to do. Then, of course, it would be nice to have estimates for the rate of convergence, which might also tell us something about this thing at the boundary, that this really goes to 0. Then, okay, one question which I might also be interested in is whether YNs are still asymptotically free from deterministic matrices, because that is what happens for the orthogonal invariant matrices. Okay, but this is a question from free probability. Then one could think about generalizations of this to random tensors. Random tensors are quite active at the moment. Okay, and then maybe, yeah, interesting is also to clarify and look into the relation of this with things which are going on in statistical physics about this symmetric simple exclusion process or the eigenstate thermalization hypothesis. So in particular, there are works of, on one side, Werner and Husrein, on the other side by Farah, Pushan, and Papaladi, who in a sense are looking also on situations like this, where actually you allow more general that the cumulants of the entries of your matrices, they depend on the indices. Okay, and this actually in free probability language would be that you go over from scalar valued free probability to operator valued free probability. You know? This is something which we still want to understand and work out. I mean, here in these papers out, they are more on the physics level, but still they go very much in the same direction. Good. Okay, thank you.